Okay, welcome back to Fluid Mechanics class number 4. This is video 3. This is the second example. In the previous example, we did a vertical surface. This time, we're going to cover an example that has a slanted surface, an inclined surface right here. So here is our example problem right here. Boom. All right, so this is from the Munson book, and it's problem 2.82, and we have a structure right here. This thing is attached to the ocean floor, right? So this whole thing is attached to the ocean floor, and it's got a hatch on it with this little hinge that's pivoting right here, and this thing is arranged so it's at 30 degrees, and there's air pressure inside here. It's attached to the ocean floor as shown. This is a 2-meter diameter hatch, right? So this is round. We're just seeing the side of it. It's attached to an inclined wall and the hinge on only one edge. So I don't know how they did that, right? You know, I'm trying to picture that, but it's got like a hinge that's like right there somehow. Maybe must have like a little flattened area to be able to have a hinge on it, right? So we're looking down at the thing right there, right? Determine the minimum air pressure in here, and they're calling that P1, within the container that will open the hatch, and neglect the weight of the hatch and the friction of the hinge, right? Ooh, come on. We need you to focus. Thank you. All right. So I think a good start is to draw an FBD, a free body diagram of this arrangement. I wish I had my straight edge with me, but he seems to have disappeared and walked away. I don't know. I usually have a lot of them. But anyway, so we're going to kind of wing it here with our straight edges here. We'll declare an FBD, and we will draw the thing fairly close to what it's supposed to look like. There, it actually looks more like 45 degrees than it looks like 30 degrees, doesn't it? So here's the hatch, a hinge, and we're going to have reaction forces, and I just always draw them in the positive direction. So I'm going to call that, still call it O. That's good by me. So here's my horizontal reaction force, and here's my vertical, Rox and Roy. And the air pressure is going to act on the center of this, whereas the liquid pressure is going to act somewhere below, right there, right? So the air pressure, which I'm going to call it FA, is acting like right there, which we know is going to be, we know that to be 1 meter, right? Because that's right there, it's 1 meter. So maybe I'll write even 1 meter right in there because it's halfway down. Whereas this one right here, this is going to be a little bit lower, right? Still perpendicular though, right? And FR is like right there. And we don't know this distance yet right here. Now, remember when we're doing a problem where it's slanted, that what we do is we draw a line that's in line with the incline, and we set this as the origin, right? And so, and now we have a coordinate system that's going to come down right here. And what we're looking for is, maybe I'll draw it a little bit lower. Right there is, this right here is, we're going to call that YC. But what we really want to have is the lower one, YP, is what we're going to be looking to apply. But then we have to remember, it's, you know, we're not applying that load right there. We're on our free body diagram, it's just going to be the distance between here and there. So they happen to be showing that the top of this is 10 meters below the surface. So that's going to be something to keep track of, right? We have to think our way through this. We don't want to just like throw stuff inside the equations. We actually want to try to think our way through the problem. I'm going to go ahead and write into the sum of the moments about O, set it equal to 0. And so for FR in this case is doing a counterclockwise motion, so it's going to be positive, so it's FR. And this distance right here is going to be that YP minus a distance that, say, was from here to the hinge, right? And that, so I'll say YP minus, and that distance is going to be the 10 meters divided by the sine of 30. right? So that's gonna. So what we're doing is we're taking this distance right here. What is the distance from the origin to the hinge along this line? And it's going to be this divided by the sine, and that will give us, right, because this is the side that you'd say that this is opposite from the angle right there. So that means that's why we're using sine. But we're trying to find the hypotenuse, so that's the reason why we divide. So we're going to take 10 and divide by the sine of 30. And that's going to give us these two things. Is going to give us this distance right here. And then now we need to get the other force is going to be the force of the air. So that's going to be, and by the way, that's going clockwise about this pivot point. So that makes it minus. And the pressure is what we're trying to find. And the area, so we're going to have pressure times area, right? It's going to be the force. So it's going to be pi over 4. Times, I think this is a 2 meter diameter squared, right? And now we need to get the distance from here. Whoops. One second. I'm not trusting what I have written down here. Why did I do it that way? This should just be 1, right? We should just have a distance of 1. I'm looking through my notes here. And yes, this should just be 1. It's obvious it should be 1. I don't know why I went through all that trouble. But must have had a good reason. I went through a lot more rigmarole, which is a great word. But we know that the center of this to here is just 1. So we didn't have to do whatever I did up above. That was really silly. Anyway. So I'm just going to leave it like there. Forget it. Okay, so now we need to find FR and YP, and then we can find out what that pressure has to be. Why did I make that little mark on the screen just now? Doesn't matter. Let's get back to this. All right, so first off, I want to find out what Y... no, I'm okay with that. I don't need that. I didn't need it. All right, so... I do. Okay, so I need to know what YC is going to be within... my FR equation. So YC is this distance from here to the center, and it's very similar to what we just did a second ago. We're going to figure out, because it's 30 degrees, that this right here is going to be 20 meters, right? But let's just go ahead and pretend we didn't know. So we're going to have that distance is going to be this divided by that, right? And that equals 20. But then we also have, that's just the hinge. Now we go one more meter. So just add 1 to it. And what we end up finding, we get 21 meters. Great. But we needed this because the next equation that we're using here, FR, we have gamma. Oh, and by the way, I think we ocean floor. So just as a little trap, that means this is going to be salt water, right? Be careful there. That's going to be salt water. And YC, that's the reason why we use that thing, times the sine of theta times A. And so if we're in meters, so we look up what salt water is from the table that's available to us. And I would use the one that's in the exam equation sheet for the material, fluid material properties. And these units are kilonewtons per meters cubed, right? So we're going to stick with that. And so our depth is 21 meters, or not depth. That's going to be this right here. And then once again, we're using the sine of 30, right? So that's actually just going to make the thing just, kind of go back to where we had. No, it's still okay. And then the area is pi over 4 diameter squared. So it's 2 squared. So from this, we're going to get 333.2 kilonewtons is what that FR is. Now we need to use this equation YP, right? That's what we have to find. YP is going to be IC, right? So the area moment of inertia about this axis right there, right? And divided by YC and A plus YC. So that's going to be equal to pi over 64 times 2/4, right? That's an equation that we can remember, right? Pi over 64 times d, the diameter fourth, divided by YC, which is 21. And then also divided by pi over 4 d squared, or 2 pi over 4, 2 squared, plus YC, don't forget that, 21. And what we're left with is a 21.01, and because it's so small, we're about to, this is so very, very close. Let's give an extra sig fig, all right? So, you know, we don't want to round down because it would almost be identical, and that would mess things up for us. So I went to an extra sig fig right there just to give a nod. Now we can plug these values into this right here and find out what that pressure is. So we're going to plug that in and that in, this value and that value. Be careful with the kilonewton stuff right here. We want to make sure that we pay attention. But I think our units are going to end up with being kilonewtons per meter squared, which we're going to know is a kilopascal. So plugging back up in, let's see, I got to do what I said I was going to do. I got 333.2, and then we had 21.012 minus, and that ends up being 20 right there, so we can go ahead and say that we know that. And subtract out, we have P times that, and then have pi over 4 d squared, and we probably might have been smart at one point to just find the area so we didn't have to keep writing that down, but we did anyway. And then we have, that's just 1, right? We established that was just equal to 1. Equals 0, and what we find, we get the pressure is going to be 107.3 kilonewtons per meter squared, and we know that's the definition right there. That's going to be a kilopascal. So the pressure is 107 kilopascals. Ta-da, the end. And so now we're going to go move on in the next video, which should be, what, video 4, I believe. And so that's going to be covering hydrostatic forces on curved surfaces. That's actually a pretty easy one, although I see what I did here. Okay, so see you soon in the next video.